A dictionary isn't frozen once you build it. You can add new entries, change existing ones, and delete them, each with a single direct line of code. In this video, we'll take one dictionary of student grades and change it 3 ways. Watch every change land in place, and then meet the in operator, which hides one genuinely surprising rule. Here is our dictionary, grades. It maps 4 students to their letter grades. Anna to B, Matt to A, John to B, and Katie to A. Now suppose Grace joins the class, the same Grace who raised a key error last time we looked her up. There is no slot for her yet. To add her, we take grades, and at the key Grace, we assign the grade A. That is exactly the syntax you would use to change an existing element of a list, but the key Grace is not here yet. So Python does the simplest thing. It does not find Grace among the keys, so it just creates the entry. No checking whether she already exists, and no loop. One line adds a brand new route to the table. Now watch what happens when we assign to Grace a second time, this time the grade C. The syntax is identical to adding her, but Grace already exists as a key, so Python does not make a second Grace. It finds the key that is already there and overwrites her value. The A becomes a C, and we still have exactly one Grace. That is convenient, but it is also something to watch for. Assigning to a key that already exists silently replaces whatever was there with no warning. Deleting works differently. To remove an entry, we use del, spelled D-E-L, naming which entry of which dictionary to drop. Here we delete Anna. That completely removes the key Anna and the grade tied to it. Anna's whole route disappears from the table. Here is the thread running through all 3 operations. Adding Grace, changing her grade, and deleting Anna each mutate the original dictionary. Adding Grace did not hand back a fresh copy with Grace in it and leave the original untouched. It changed the one dictionary that grades points to right where it sits. The same is true for the overwrite, and the same is true for the delete. There is a single dictionary object, and every one of these operations reaches in and edits that object in place. Often you just want to know whether a key is present before you touch it. The in operator answers that. First, we reassign grades back to the original 4 students, so we have a clean slate. We have already used in to test whether an element is in a list, whether a character or substring is in a string, and whether an item is in a tuple, and it works on dictionaries too, with one crucial catch. On a dictionary, in checks only the keys. Asking whether John is in grades gives true because John is one of the keys. Asking whether Daniel is in grades gives false, since Daniel is not a key. Now the surprise, asking whether B is in grades also gives false. The letter B sits in this dictionary as a value. Anna maps to B and John maps to B. But it never looks at the values, it only ever asks about the keys. Let's put that key-only rule to work. Here is an exercise. Write a function finding L that takes a list of dictionaries and an integer k and returns true if k is a key in any of those dictionaries, and false otherwise. Suppose we have 3 dictionaries. D1 maps 1 to 2, 3 to 4, and 5 to 6. D2 maps 2 to 4 and 4 to 6. D3 maps 1 to 1, 3 to 9, 4 to 16, and 5 to 25. First, we search the list for the key 2. D1's keys are 1, 3, and 5, so there is no match there. But D2 has 2 as a key, so the answer is true, and we can stop the moment we find it. Now search for 25. Look carefully. 25 does appear in D3. In the entry, 5 maps to 25, but there it is the value, not the key. Nothing is keyed by 25, so the honest answer is false. Here is the solution. We loop over each dictionary D in the list. For each one, we test K in D, which, as we just learned, checks that dictionary's keys. The moment the test succeeds, we return true immediately. That return does double duty. It stops the loop and hands the answer straight back to the caller. so we never waste time checking the rest. Now look at where return false sits. It is outside the loop, not inside it, and not inside the if. That placement is the whole trick. We reach return false only after the loop has walked through every dictionary, and none of them contain the key. Put it inside the loop instead, and you will give up after the very first dictionary. There is another valid style. Set a flag called found to false before the loop, flip it to true inside when you get a match, and a return found at the end. Both work, but the early return version is the more Pythonic one. One last property worth internalizing: you should treat a dictionary as having no order. A list is an ordered sequence, its first element at index 0, the next at index 1, and so on. A dictionary is not that. Modern Python does keep entries in the order you inserted them, guaranteed from Python 3.7 onward, but older versions gave no such promise, handing entries back in an unpredictable order. So if you want code that runs correctly everywhere, write it assuming no order exists. It costs you nothing. And because you cannot rely on position, a great deal of dictionary work means visiting every single entry in turn, and that is the one dictionary skill we still don't have. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.